Hello, I would like to talk today about least squares in a rather informal way and introduce you to a tool that is very handy for solving a large set of problems, especially state estimation problems. That's what we will be using it for here. So just as a reminder, we start out with that because we want to use it as a tool to address the simultaneous localization problem, and we are especially looking here into one variant of the simultaneous localization mapping problem, which is a graph-based approach. So where we use a graph consisting of observations and controls and try to treat this as an optimization problem. And for that, we will use the tool of least squares. So graph-based SLAM is nothing else than a least squares approach to SLAM. And in order to understand how that works, I would like to introduce you today into the least squares problem. So what is least squares for? It is a general approach for computing a solution of an overdetermined system. And it does that in a way that the small mistakes that we do everywhere is minimized, and we are minimizing the squared errors, or the sum of the squared errors. So let's take a very concrete example first. What can be an overdetermined system? So for example, we have a set of parameters that we want to estimate, and we have a set of observations that we get which tell us something about those parameters. And then it is often the case that we have actually a large number of those observations because we want to estimate those parameters as good as possible. So we have more observations than parameters, or more information in those observations than our parameters. And then, given that we have always noise in our observations, we will not find a perfect solution. We will not find the set of parameters that brings all the whole system to zero mistakes. So there will always be small noise values remaining. And we're trying to find parameters that minimize the sum of those squared errors. So overall, we say we have more equations than unknowns. Unknowns are parameters. Equations are the things that, at least in the way we use least squares, stem from our observations. And we want to find the unknowns or parameters so that the sum of the squared errors is minimized. And that's a standard approach. It is out there since more than 200 years. It's very frequently used in a lot of engineering problems, and we often use it here in order to estimate model parameters given a set of observations. So in the context of the SLAM problem, our observations can be sensor observations like camera data or laser rangefinder data, but also observations from our odometry encoder, so how the wheels move. And then the parameters we want to estimate are often the position of the platform in the environment at different points in time, as well as the location of, for example, 3D landmarks in the environment. So we're trying to estimate those parameters. Where are we? What does the world look like given observations? And something, the way you see how I formulate the problem, that's something that we have been doing since quite a while, taking those observations to estimate certain parameters of the state. So the least squares approach, as I said, is around since quite a while. Carl Friedrich Gauss, at the young age of 18 years, developed this approach, and it has its first showcase a few years later in order to estimate the future location of the asteroid Ceres in 1801, where it first showcased that is a good tool for solving relevant problems. Again, we will be using it here in the context of the simultaneous localization and mapping problem, and using it in order to build maps is something that has been there from the very early days on. Even Gauss himself used it in order to build maps or measure distinct points in the space. So it's not a very new problem. The only way which is new in robotics is that the way, what kind of constraints, what kind of observations we have, that we are interested in certain things like doing this very fast, treating this as an online problem, not as an offline problem, having other data association challenges in there. So there are a lot of things which are kind of special in the way we address the SLAM problem, but the overall idea of using the least squares approach for solving this mapping problem is something which is around there since quite a while. Okay, so let's get slightly more concrete. How does that look like? So I formulate it in a way that we say we have a given set of observation functions, which are here called f. So these are those f's. And what this observation function does, it basically computes an expected observation or a predicted observation, assuming that it knows the state. So the state, or our unknowns, are this is variable x here, and we say, given that we know what the world looks like and where we are, for example, we can actually compute what we are expecting to observe. And this is what this function f does, my observation function. So f tells me what should I observe. And then we have our zi, which is the actual measurements or actual observation. It doesn't have to be necessarily direct observation of the state x, but the measurement is strongly related to the state x, so that that we can relate the state x through this observation function with our measurement. And this exactly happens with our z hat. So z hat is our predicted observation, which uses this observation function, as I described it, to predict what we should see given we are in state x. Okay? So the key idea is then to take what we are expecting to observe, assuming x is correct, and what we are actually observing, so the observation that we're actually obtaining, and then relate them with each other to see how should x look like so that the observations are as similar as possible. So the goal of the overall approach is to estimate the state x, which best explains my set of observations. So typically we have more observations. Let's say we have n observations over here from 1 to n, and then we want to find the n which best explains our observation 1 to n, and we do that in a way that we are looking to the mismatch between what we actually observe and what we are expected to observe, and then look into the squared error of that. So we can also explain in a graphical way in a quite easy form. So here x is our unknowns, our parameters that we want to estimate. Then we have our observation function, which tells us what should we see given the state of the world is x. And this gives us our predicted observation. These are those z's with a small hat on top of them. And this is basically what we as a user need to provide. So we need to provide this function to compute the predicted measurements. And it depends on the sensor, for example, that we're using. And then we obtain our real measurement, which of course depends also on the sensor, but now on the actual physical device and not on our model of the sensor. And then what we are doing, we are basically comparing those pairs. So z hat 1 with that 1, z hat 2 with that 2. And we typically compute differences between them in the easiest form, and then square those differences. What we then try to do, if we would sum up all those differences, square differences here, into a sum, that we want to basically change x so that this sum gets minimized. So it's a problem where we want to find x so that the discrepancies or differences between the predicted measurements and the real measurements is actually as small as possible. Again, a small concrete example. Assume x are the location of 3D points or 3D features in the environment. So these x is basically says, whatever, at that certain location there is a point and it has a coordinate, whatever, x equals 10, y equals 2, and z equals 3, just as an example. And then I have observations, in this case, let's say a camera, which is positioned somewhere in the environment, and then the observations are basically those points projected onto my image plane. So I get a pixel coordinate for each of those 3D features. And what I, as a user of that algorithm or designer of that algorithm, need to do, I need to specify this observation function f. And this observation function, in this case, describes the projection from the 3D world onto the 2D image plane. So I actually need to describe how a point is mapped into a pixel coordinate. So given that I put in a random coordinate, let's say 1, 1, 1, then I need to, this function tells me to which pixel coordinate this point 1, 1, 1 will actually be mapped to. And then I can compare my actual observations, so what the camera, the pixel location that I actually got in my real image, with the pixel location that I computed using my function f. And then I want to try to change I'm basically shifting around the location of those points in the 3D world so that this difference get minimized. And the question, how do I actually move those x around? How do I vary this x? This is what the approach basically tells us. Okay, so now let's get slightly more formal and see how that is actually set up. So everything boils down to computing this error. So the discrepancy between the actual measurement and my predicted measurement. And in my notation here, this is typically always called EI, so because we have multiple of those observations, so this is the index I. And this error function depends on the state, so it depends on my current configuration of the parameters, so my current vector x. And it's, again, the observation are actually obtained, so there's nothing I can change in here because this is what I actually observed, minus this function which takes in the parameter x. So if I change the x in here, this will lead to a change in this f of x here, so it will lead to a different difference between those two. So this is just kind of the vector difference. So this is a bold E, so this is a vector estimating or referring to the difference between the actual measurement and the predicted measurement. And then under the assumption that we have normally distributed variables with zero mean, so there's no bias in there. So it's basically just, let's say, a Gaussian noise that my sensor provides. Could be the pixel coordinate in the example of a camera, or could be a difference in range for laser rangefinder, for example. And we also assume here that we know how good our sensor is. So we have a notation of uncertainty of the sensor, which is expressed in an information matrix, here our omega I. So every observation can, for example, have a different information matrix. And the information matrix is the inverse of the covariance matrix, so it basically tells me how much information does this measurement actually convey. And then we can turn the error vector here into a squared error by using the error vector, so this is the same EI, transpose it and multiply it with the I. So we square it. And what we also do, we put the information matrix in here as a weight. Okay? So this is kind of, we already have a weighted least squares here. If we say all observations have the same uncertainty, then we can actually also leave that out, and then we just the error function itself. Okay, but here we typically have or assume to have some notation of uncertainty, so we will keep this information matrix with us all the time. And this is the encodes the uncertainty of the individual measurements observation that we have. Okay, and then this EI, non-boldface, is a scalar value, and this describes us the error that one single measurement actually generates, and it's the squared error term here for that single measurement I. Okay, given that we have more than one observation, so we have multiple observations, we are actually interested in minimizing the sum of all those squared errors. So our desired state x star, so the x that we want to compute, our optimal state, is computed by minimizing a function f of x, or capital F of x, which is here the kind of global error function, which is a scalar, and it can be expanded by just being the sum of the individual error terms that we just computed on the previous slide. So these are the squared error terms, which are also scalars of the individual measurements. And we are simply summing over all measurements. We can again expand that further and say this is the sum over the error vectors times the information matrix times the error vector, and we are summing over all of them. And this is the function that I want to minimize, so it's the sum of all the individual observations, or the error that results from the individual observations obtained through comparing the actual observations with our predicted observations. Okay, so the goal is then to find the minimum of that function. So the parameter x, so we are varying this x, and we are interested in the state x that is the minimum of this function, a global minimum. And in general, this is a complex problem, especially depending how this function f actually looks like. So in practice, we need numerical approaches in order to solve that problem. And typically, this function f is also a nonlinear function. So this can lead to situations that we may not even be able to find a good solution for our problem. And so we need iterative approaches, but still it's not guaranteed that we actually find the minimum all the time. What we typically need is a good initial guess. So we need to have a good initial value for our x. If we are very far away from our initial solution, then we, in most of the cases, will not find a reasonable solution, at least for most realistic real-world problems where these functions are often nonlinear. And we also assume that our error function is, let's say, reasonably smooth in the, let's say, local neighborhood of the actual global, hopefully global minima, where our initial guess is close. So we assume to be kind of close enough so that we can actually, through an iterative error minimization, actually end up in the minimum error configuration. Again, in general, there's no guarantee that we actually find the global optimum in the general case. There are several variants of this problem where I can say something about convergence guarantees or about guarantees, but in the general form, this is not possible. And what we are doing here, we are solving this problem through an iterative least squares approach, so iteratively computing local linearizations of this function, and then treating it as if this function f or the error function e would be a linear function, and then kind of going step by step iteratively towards the minimum. Again, no guarantee that this actually works out. Okay, so what do we need to do in order to solve this iterative local linearization? So the first thing we need to do is to compute a linearized variant of our vector error function ei. And so we assume to have an initial guess, and what we need to do, we need to locally linearize around the solution that we have this error function. And then we take this local linearization, and through the equation that we have, we square it, and then get our squared error function. Okay, and then what we need to compute, we have a quadratic function in the end, and what do we need to do in order to compute the minimum of a quadratic function? That's something that you may know from your analysis classes in school. So we typically compute the first derivative, we set the first derivative to 0, and then solve the remaining system, and then get a solution for the minimum of that function, this quadratic form. However, we have the setup here that this quadratic function was an approximation in the first place. So we are basically going back to the start and saying, okay, assuming that my solution got a bit better than before, let's simply do the same procedure again. So we are again computing the local linearizations, approximating the general error function by a quadratic function, computing the minimum, and then we actually iterate this process. Okay? So let's dive into the steps how that actually works. The first thing we need to do is to linearize our original error function. So because this function f is in general nonlinear, and we need to compute an approximation for it so that we have a linear function, so that in the end we obtain actually a quadratic error term. And this is for doing this, we do something which is called a Taylor expansion. And for computing the Taylor expansion, we need to compute the first derivative of our function e. So we are saying our function e is now slightly written as x plus delta x. And this x is now our initial guess. So it's a kind of a constant in this current iteration. And this delta x is actually our variation around this initial guess. So this is 0 if we are at the initial guess, and typically takes values slightly larger or smaller than 0, and expresses the variations around this initial guess. And so how does this actually look like? So this is the error term at the location of the initial guess. So ei of x. But this x here is now a constant because it's our constant initial guess. So this term also is a constant and typically abbreviated with ei in the remaining. So just drop the of x of the initial guess just to have a more compact notation. And then we have a sum of this absolute value constant offset, so to say. And this here, this j, is Jacobian. So the first derivative if we leave the one-dimensional world, so to say, and multiply this with this delta x, which is my vector, which is the variation from the initial guess. So this is a kind of a small error vector. And this is basically a linear function. So we are having our linearization point and have a linear function in the neighborhood of this linearization point. And how is this Jacobian computed? Just as a reminder, that's something that I generally assume you to know, how to compute Jacobians and deal with basic linear algebra, but just as a short reminder. So this is a matrix, and we have in the dimensions the number of dimension that my parameter x has here, and down here we have the number of dimensions of my function f that I'm actually for which I want to compute the Jacobian. So this is a partial derivative of the first component of the function derived with respect to the first dimension of x. This is again the first dimension of this function f derived with respect to the second dimension of my vector x, and so on. And down here, I'm basically keeping the dimension to which I compute the derivation, so the x1 constant, and changing the first dimension of the function, second dimension of the function, third dimension of the function, and so on. So it's a matrix of my partial derivatives. Okay, so this is now an approximation of my error function, of the individual error function for every single observation. And it is now from the originally nonlinear error, it turns into a linear function. So this is a linearization. So this is an approximation here. That's important to note. This is an approximation. Okay, so what we now can do is, given that we have the individual vector error function linearized, we now need to compute the squared error term. So using this linearized function and compute the squared error of this linearized function. So this is now ei of x plus delta x as before, but again, note that this ei is now the squared error term. It's not a bold face character. And now we are putting in first the definition. How was this term defined? So just kind of writing down the definition. This was the error in vector form transposed of x plus delta x times my information matrix times the second error term again. So this was just the definition of the squared error multiplied with the information matrix. So our information about how much we can trust our observation, or how uncertain this observation actually is. So and what I'm now doing, now I'm using this Taylor expansion that I just computed, and I'm replacing this term and this term over here with my approximation from the Taylor step that I just did on the previous slide. So what I can do now, I can say, okay, this is now not exactly the same anymore, just approximatively the same. And this is here now my Taylor expansion. So this ei, which was just the error value in my linearization point, and then plus the Jacobian times the deviation in the Jacobian. And then I can just expand this expression over here, and then I will get a number of different terms. This is just obtained by expanding those brackets over here. And then we see we have some terms where which are independent of x, which is this term over here. We have some terms, which are those terms over here, where we have a linear dependency in my unknown delta x here and here. And we have a fourth term over here, and this fourth term has quadratic elements. So I have delta x and delta x appear twice in form of a multiplication in this equation. So what I now can do is I can take this term and rearrange it a little bit. So this is just kind of copy-paste what we had on the previous slide. And then I can just do a small rearrangement of these terms over here in order to group them and basically introduce a new variable to make my notation easier. So I have a kind of a constant term, which takes this c. This is ci. This is basically constant elements of this expression. Then we have a second term which we regroup, which is contains the elements here of my error vector, and these are basically all the linear elements. So this is 2 times, and then this expression ei transposed omega I ji, and these elements here I replace by bi transpose, so by a vector bi, so this is a vector times delta x. And here is a quadratic term, and again, all the quantities which do not depend on my delta x, I summarize in one variable here, hi, and then I have a quadratic element in here. So what I then can do is I can just rewrite it using my c, b, and h, and then the final equation looks like it's ci plus 2 times bi transposed times delta x plus delta x transposed hi delta x. So my quadratic term over here, my linear term over here, and my constant term over here. And again, I was introducing these variables and was packing basically everything into those variables where there was no dependencies on this delta x. And so far, this was just a rearrangement of the individual error terms. So there was no black magic ongoing. The only approximation I did was putting in my Taylor approximation, and then I was just rearranging those terms. And this was done now for one squared error term for one single observation. And again, overall, I want to do this for all the observations. I'm looking to the sum of all observations. So I can use the same thing for the global error term. So the global error term f of x initial guess plus delta x, my variable, is just the sum over all the individual error terms. So again, this was the result of the previous slide. This is the term for one single constraint or one single observation. And what I then can do is I can just move the sum into the sum element here into the individual sums here in the bracket. So I have the sum over all ci's, I have the sum over all bi's, and I have the sum over all hi's, because my delta x, of course, is the same in all the sums. And so then I have a sum element which takes all the constant elements into account. I basically here have a part in a sum which takes all the coefficients of the linear term into account, and I have basically all the coefficients for the quadratic terms, so that I can again do the same rewriting, defining this as a c, this as b, and this as h without the index I, because now the sum of the individual terms. And just by a simple rewrite, I can then express the global error as the constant c 2 times b transposed times delta x, so this b is a vector, plus delta x transposed times h times delta x, and this h is a matrix. Okay? And the b and the h, which are the kind of important elements that we'll need later on, are actually defined here. The one is just the sum over all the coefficients of the linear term, and the other is the sum of the coefficients of the quadratic term. And these b and h are elements that we will actually need later on. So as a result, what we have so far, we linearized our individual error terms, the vectors, and then computed the quadratic error terms, and it turned out everything turns into a large quadratic form. So our overall function that we want to minimize is expressed over here, and our goal is to minimize this overall function. And again, how do we compute the minimum of a quadratic form? So you may again think about how do we compute the minimum of a parabola. When you think about analysis classes you had in school, what you typically did is you were computing the first derivative of this function, and then you're setting this first derivative to 0, and then you have an equation that you solve, and you solve it with respect to x, and then this tells you where your minimum is. And we are basically doing the same thing here in this high-dimensional space. What we need to do is we need to compute the first derivative of this quadratic form. Then we will set this first derivative to 0, and this will lead us to a system of linear equations. And then we have to solve the system of linear equations to come towards our solution. So it's basically the same thing what you still probably know from your classes in school, except that we don't do this for the 1D case, we do this for in an n-dimensional case. But the overall idea actually stays the same. Okay, so assuming we have our quadratic form, here x transposed, or a general quadratic form of this form. We also have a constant here, but the constant is not really relevant for us because the constant will anyway be gone in when we're computing the first derivative. And then the first derivative of this quadratic form is given by h plus h transposed times x plus b. And so this is kind of for because we are in the form of where h is a matrix and not a scalar, as you may know or remember it from school. So where you would have this quadratic term would give 2 times x times the coefficient, and this will give simply the coefficient. So the coefficient stays the same except of the transposition. And here this 2 times h is h plus h transposed because we are in the matrix form, but you can directly see the analogy to the one-dimensional case. So this is now, we know how to compute the first derivative of this quadratic form. Will give us this derivative. So we can just take it and apply it to our problem. So again, this was our quadratic form. And then we compute the first derivative of this quadratic form. again, the C vanishes because it doesn't depend on delta x. We have here 2 times b times the transpose times delta x. And if you go back, this was this constant term over here. This turns just into b. So in this case, this is 2b, because we have the factor 2 is still in here. So this part of the first derivative will give 2b. And then we have the part delta x transposed h delta x. This will give us 2 times h times delta x. Okay? And so this is now our first derivative of our error function. Okay? So the next thing we need to do, we need to set this element to 0, solve it, and then we are done. So overall, this means we're computing the first derivative. That's what we just did in the previous slide. We are setting it to 0. So we say 0 times 2b plus 2h delta x. Of course, you can see immediately the 2 vanishes. We can move b to the other side so that we will have a system in the end that we need to solve, which is h times delta x equals minus b. And here you see this is a system of linear equations. And now what we need to do, we need to solve this system of linear equations to get the solution for our increments. And I'm just writing this here now by inverting h. So we're basically multiplying h inverse from the left-hand side. If we do this, then this turns the identity matrix. Delta x remains. And here we have minus h inverse times b. And this gives you the solution for your increments. In reality, you will not compute this inverse explicitly. There will be other ways to do this. But this is kind of this one step to move these delta x more towards the right solution. Okay? So this was kind of one step of our approach. And in general, we need to iterate this, and this gives us the Gauss-Newton solution to this. So what we are doing in every step, we are linearizing around the current initial guess that we have x for each measurement. So this was this first term over here. We need to linearize all our error functions. And we need to do that over and over again because we are changing the initial guess. The initial guess is always the solution of the previous iteration. So we need to do this relinearization for every iteration. Then we compute our terms b and our terms h by basically summing over all error functions, multiplying the value of the error function, the information matrix and the Jacobian, or here Jacobian transposed information matrix Jacobian. So we use this to compute our b and our h. This gives us the elements for our linear system, and we solve this linear system and then say our new x, our new initial guess is the old initial guess plus my delta x star that I computed. And this is an iterative approach. I'm iterating this until all those delta x are basically 0 or very close to 0. And then I'm basically hopefully converged to my global optimum. Again, no guarantee that it is the global optimum, but there is the hope, if our initial guess is good, that we will actually end up at the global solution. So this was a very brief and informal introduction to least squares and the least squares approach that we will be using in this course. Next, I can show a very short example, a very small example, a very simple example, how we can actually use this in order to perform a state estimation problem. And I want to use the example now not using SLAM, but let's say odometry calibration. So again, as a short reminder from last year, odometry is basically the position of our platform computed by counting the revolution of the wheels. So when we have typically odometry measurements, which basically tell us how much did we actually move forward. And typically you have systematic errors in this process. Let's say one wheel is has different air pressure, for example, slightly larger or smaller, so you will experience a drift to navigating one of the sides, or not everything is geometrically in a perfect shape. And what we want to do is we want to kind of find a way, using the least squares approach, for minimizing this or eliminating this systematic errors through a calibration procedure. And that's what we want to do. So what we assume here, we have, let's say, a sequence of a mobile platform driving around. We have those odometry commands, and we additionally have ground truth information. So we know where the platform actually moved to. And this ground truth information can be made available by either using certain sensors which are on board, by running a SLAM system, by using an external motion capture system, by using a LiDAR scanner we have installed on top of it, or by externally tracking that system. That's something we don't care. We just assume that we have ground truth odometry available. So we assume we have the odometry that we measured, and we have the ground truth odometry available. So this U star I expressed here. So just we have an external tracking system for that. And then we take a very, very simple function. Our assumption here is that we can compute a corrected odometry command, UI prime, which is just a 3x3 matrix multiplied with our obtained odometry command. So this is basically our correction function, which performs the correction and turns the uncalibrated odometry into the calibrated odometry. So this is now a very simple function, but it's pretty good for us for using this as an example on how to use our least squares problem. So we obtain our correction function f. In order to do that, we need to find our parameters, parameter vector x, which is kind of how does this function look like. So these are the parameters of this function f, and that's my unknown that I actually want to estimate. So let's say first, what is the state vector here? Okay, the state vector is this calibration function that I want to compute. And so this state vector is then these 9 elements which are used to design this function, right? So these are exactly those elements here. So my state vector is simply a 9-dimensional vector containing these 9 elements of this function f. Okay, so what is my error function? Again, the error function is discrepancy between what actual state is and what I think it is with my function. So between the truth, or what I actually obtained, and between the my model that I'm using for predicting that. So in this case, the error is simply given by what the actual position of the platform was, minus this function, this calibration function, times u, my my information that I actually get from my system. Okay, so what I then need to do is I need to, the next step to do, I need to take my error function and compute the first derivative of my error function. So how does this actually look like? So what I need to do is I need to take this and derive it with respect to my parameters. So I need to take this function and derive it with respect to the individual dimensions of my state vector. So it's basically dE by dx, and this is dx. So I need to derive this expression over here with respect to all my unknowns. So my Jacobian will be a matrix which has 9 columns, because we have these 9 dimensions over here, and there's 3 rows, because this is a 3-dimensional function. Okay, so will have 3 rows and 9 columns. And it actually turns out that this is a very, very easy form. So everything where nothing is written here, it means that there are 0 elements, because what happens, I have my this term is my vector, my ui star, which is constant. I'm multiplying this ui, let's say, with respect to x, y, and theta in the 2D case. And I need to multiply this term with this matrix over here. So if I then compute the first derivative, for example, for this element, computing the first derivative with respect to x11. So this term is constant. This term over here will be multiplied with the first element of this vector, so ui x, the first component. And this will be linear multiplication with this x11. And then the second dimension is with this one, and the third dimension with this one. But they're all independent of x11. So if I compute the first derivative of this term, the only term that will remain is uix, so the first component of this vector. And this is the same for y, theta, and so on. So I will have here non-zero elements, which are basically the elements of this vector over here. And all the other elements here will be 0, because there's no dependencies of this variable. So all those elements are 0 over here. And what I additionally see in this Jacobian is that there is no dependency on x. So an x is never showing up in this Jacobian. And this is something which is normally not the case, but here it is the case. What does it mean if I compute the first derivative, and the first derivative does not depend on the variable anymore? It actually means that my function was already a linear function beforehand, because I basically have a constant first derivative. So that means that I already have a linear function, and it means that I don't need to relinearize. So if I run my least squares approach and compute a solution, and I would repeat the iteration again, I would get exactly the same quantities in there. Okay, so the initial guess doesn't matter. So it means I just need one single iteration, and then I'm actually done and can compute my solution. So now I have my Jacobian, and then it's a standard procedure. I just compute my h and my b, I get a system of linear equations, I solve it, and this gives me my state vector, this state vector over here. And then I put the state vector putting into my calibration function, and I obtain my solution. Okay, it's rather straightforward, and the fact that the Jacobian here is independent of x means that I don't need to iterate over this process. So a few questions you may ask yourself. How would the parameters of this function actually look like if odometry would be perfect? So how should this calibration function look like if my odometry would already be perfect? Okay, let's go back and look to this function over here. If my odometry is already perfect, that means this ui is already this ui star. And then, in order to bring this expression to 0, this matrix here should actually be the identity matrix, right? So if I have the identity matrix over here, here 1 elements and everything else is 0, this term would always be 0, and I have no error remaining, and I found the minimum of my function. So that would be the case if odometry would be perfect. The next question is, how many measurements do I actually need to find a solution to my calibration problem? And here we need to look a little bit, how many unknowns do we have, and how much information does every single observation actually provides us. So how many unknowns do we have? We had 9 unknowns. This is 9 elements of this 3x3 matrix. And with every observation, we basically have a 3-dimensional observation. So at least, at minimum, we need to have 3 observations, because we have 9 unknowns we need to fill. Every observation gives us basically 3 equations, so we need to have at least 3, if not typically more, equations in order to come up with a good solution. The next thing is, this matrix H is a symmetric matrix. Why is this actually the case? Any ideas why H is a symmetric matrix? Of course, I answer this question now for you. So it's because the way H is constructed, that I was it consists of the Jacobians. Let's go back so you can see it better. How was H set up? The matrix H is set up by the Jacobian transposed times the Jacobian with a weight matrix in between. And this weight matrix is the inverse of the covariance matrix, which is a positive semi-definite or matrix. And so I multiply here J transposed and J from the left and the right hand side, and just kind of a sum of all those elements. So all the individual elements will be symmetric, so that also my function H is symmetric in the end. And then the last question is, how does the structure of the measurements actually affect the structure of H? And that's something which may not be very clearly visible, but what you can maybe guess if you compute those Jacobians, and we have seen here a lot of elements in this Jacobian is 0, and if the elements in Jacobian is 0, that means there is no impact of this observation with a certain parameter in my state space. And so, as a result of this, the more a measurement will tell me about all my state vectors, the more denser populated these Jacobians will be, and this is a direct impact on my H matrix. So the sparser the matrix is, the less in one observation tells me about variables. And what we have in reality, especially in the context of the SLAM problem, especially, is that an observation only relates a very small number of variables with each other. And so it's these H matrices for the individual observations are very sparse, consist of a lot of zero elements. And this is something that we'll exploit later on in order to compute efficient solutions. I want to spend a few words now on how to efficiently solve a system of linear equations. So what we want to do is we want to solve hx equals minus b. And in theory, we can solve this, as I said before, by computing the inverse of h, multiplying it from the left-hand side. So then this will go away, and we have h inverse multiplied here from the left-hand side to this equation. But this requires a full matrix inversion, which is something you don't do in practice. So what you typically do is you use matrix decomposition techniques or other techniques for a large system like conjugate gradients. And this could be Cholesky factorization you may exploit, or QR decomposition. It depends a little bit on the properties of your system. And I just want to go through a very brief example and tell you how you can use Cholesky factorization in order to do this. If A is a symmetric and positive definite matrix, and the system we want to solve is AX equals to B. What we can do, we can use the Cholesky factorization. And what the Cholesky factorization actually does, it takes this matrix A and splits it up into two matrices. This is L transposed, with L being a lower triangular matrix. So where the upper triangle, everything above the main diagonal, contains zero elements. Or zero. And so what Cholesky does, it provides us this matrix L so that we can express A as L transposed. Okay, so what can we do now? We can actually replace this A with L transposed. So then our linear system is L transposed X equals B. And what we then can do is we can say, okay, let's multiply this L transposed with X. So L transposed X and X, because this is a matrix times a vector, and this will basically give me a new vector. So this means I can then solve the system L times, let's say, the new vector Y equals to B. And I first solve this system. So I first solve this system over here, Ly equals B, where Y is L transpose times X. And this is easy to solve because L, remember, is a lower triangular matrix. So a matrix which has triangular shapes, so you can very easily solve it, your linear system. And then in the second step, you solve L transposed X equals Y, because this is exactly the missing part that you want to solve, the replacement you did before. And again, this linear system is very easy to solve because this is now an upper triangular matrix, because it's the transpose of the lower triangular matrix. So by computing the Cholesky decomposition, we basically replace solving the one complex linear system by solving two simple linear systems. And so, of course, the main work is done within this Cholesky decomposition, but once I have it, I can very easily solve my system of linear equations. So to sum up how we use this Gauss-Newton method in order to compute a solution to a least squares problem. It's an iterative approach, and we typically start with an initial guess. So we have an initial idea on what the parameters of our system are. And depending on our actual problem, how nonlinear it is, this initial guess must be very good. Or if we basically have a linear case, then this initial guess doesn't matter because it doesn't play any role in the computation of the Jacobian. So what we then need to do, so what is the actual work that the designer of the algorithm needs to do? We need to compute the linearizations of our error functions. So we need to sit down and compute the first derivatives of these error functions. When we have these first derivatives, we can compute this quadratic term. And the key elements we're interested in this quadratic term is this H and this B. So the matrix H and the vector B. Why is this the case? Because these are the only two elements which remain when I compute the first derivative of this quadratic form and set this derivative to 0. Then I get a system of linear equations which just contains this H and this B, and I then need to solve this system of linear equations. And for that I can use, for example, Cholesky decomposition in order to solve that system. And this is actually a step which may take a substantial amount of computational resources. And then I finished one single iteration, and then I iterate. I go back to this point over here, where the solution that I computed here is my new initial guess. And I repeat this process until convergence. And this leads me to a new configuration of my state, or my parameters that I wanted to estimate, which, if converged, minimizes the squared error terms. So this was kind of a short summary on how to solve the least squares problem in very practical setup and in the way we will be using it here in the course. Before ending, however, I want to go a step further and tell you a little bit about the relation of this least squares problem to probabilistic state estimation. We started out, if you think about that, saying in this approach of what we call probabilistic robotics, we want to represent the state of our robotic system, for example, as a probability distribution. And we argued that this is valuable because we can't compute the exact values, and probabilistic approaches have the advantage that we explicitly have a notation of uncertainty that we then can exploit for state estimation, but also for action selection processes. But what I explained so far was actually, it's not directly obvious how this relates to probabilities, right? So what I actually want to do now is answer the question, how is this least squares approach relate to state estimation, probabilistic state estimation? So what's the connection between them? And for that, I want to start with probabilistic state estimation and see that through some assumption that we do, we actually end up, if we want to maximize this probability distribution, at a solution that our least squares problem actually generates for us, so that there's a direct link under some assumptions. So we start out with saying, okay, we have a probability distribution about my vector x, and typically we have a time series here because that's how we will use it in the past and we'll be using it before. We have a set of observations and controls, control commands, although those control commands can be very easily interpreted also as an observation, how I can do that. And so by just applying Bayes' rule and an independence assumption, Markov assumption, we can actually rewrite that in the form that we have some normalization constant as a result of Bayes' rule, some prior node, so this was this x0 at time 0 where we don't have any observations or control commands available, and then it's a product where we have our motion model, so everything related to u, and our observation model, everything related to z, as a product written in there. Okay, so this is kind of just expanding this term basically with product rule and applying Bayes' rule a few times and exploiting the Markov assumption. Actually similar as in the derivation for the Bayes filter. The only difference is in the derivation of the Bayes filter I was only interested in xt over here and not 0 to t, so this is actually even easier. Okay, so we have that. Now what we can do is, okay, let's have a look to the log likelihood. So if you compute the log likelihood of this term. So it means we put a log in here and a log over there. So if I compute the logarithm of that probability, then the different element, the product basically turns into a sum. So I have this log of eta, log of p of x0 of my prior, and log of this expression, and all as a sum. So this is my constant, the normalization constant from Bayes' rule. Then I have a log of my prior, and then the product turns into a sum of the log from my motion model and the log of my observation model. Okay? And now I'm making an assumption. Now I say, okay, let's assume all these probability distributions in here are actually Gaussians. So the prior here is the Gaussian, my motion model is the Gaussian, and my observation model is the Gaussian. Okay? So this is an explicit assumption. We are leaving kind of the general state estimation and making it more specific by saying, okay, let's restrict our distributions to Gaussian distributions. So well, how does a Gaussian distribution look like, or especially the log of a Gaussian distribution? So it is some constant minus the elements we have in the exponent, right? So this is x minus my mean transposed the inverse of my covariance matrix, and then again x minus my mean. And now I can actually link that and define what my error function looks like. Or I can, for now, just replace it. So let's replace this term here with E transposed. Let's replace this term by my omega, and replace this term again by EI. So I'm just basically defining those variables, but of course I'm defining in a way that I can make the link to the least squares problem. So I have my error term over here, my information matrix, which is the inverse of the covariance matrix, and my error term over here. And so this again, a squared term has exactly the same shape as the squared error that I actually had before. So if I take this, was log likelihood of a single Gaussian distribution, and plug it into my my expression that I had over here, so putting it in here, and in here. And if I do this, then I obtain this term over here, where, say, I have my error term for the prior, and I have an error term related to the odometry command, and an error term with respect to the observation, and they're all just added up times a constant factor. So if I'm now maximizing the log likelihood of my probability distributions, if I'm maximizing this term, this is actually equivalent to minimizing the error, right? So maximizing the probability distribution is equivalent to minimizing, I can ignore the constant if I think about a minimization or maximization, my prior plus the errors resulting from motion commands and the errors from my observations. So far, we didn't look into a prior before, and we didn't look into the commands so far. We basically had only the sum of the errors of the individual observations. So this means that minimizing the squared error is equivalent to maximizing the log likelihood of independent Gaussian distributions. So if we assume everything is Gaussian and we have independent observations, independent Gaussian distributions, then computing the solution to the least squares problem is actually equivalent for computing the mean, so the most likely configuration of that probability distribution. And so that's actually the link between both of them. So if I'm computing the minimum error configuration, I get the mean of this Gaussian distribution. So by performing this error minimization, I actually have a direct link to probabilistic state estimation. And there are different ways that we can compute or approximate also the covariance matrix by exploiting this matrix H that we have. So there are more links, but I wanted to show here the quite obvious and easy to derive link on how those two elements actually come together. So to sum up, what we've introduced here is an, let's say, not very formal, more an informal introduction to the least squares problem, but at a level of math of formality that I think it's good to understand what's going on, and which allows you to use this as a tool for solving standard least squares problem. If you have very special setups, you may need to dive deeper, but the majority of problem, at least in its basic form, you can actually solve with the techniques that I have explained over here. We introduced the Gauss-Newton approach as an iterative approach for solving these nonlinear problems, and the key things is we used linearization in order to turn the nonlinear error function into a linear error function, approximated by a quadratic form, and then compute the minimum. And we need to actually iterate this process due to this linearization. So we need to be clear that this linearization is an approximation of the original problem. What we also have shown now in the last minutes is that the relationship between performing this error minimization and probabilistic state estimation, so that by assumptions that we make over the probability distributions involved, we can actually show that minimizing the error is equivalent to maximizing the probability. And the least squares approach here is a very popular method in a lot of disciplines. This is not only robotics, this is basically all fields of engineering at some point in time use least squares in order to solve problems. In certain fields, it's more popular in geodesy. Basically, I don't want to say all problems boil down to least squares problems, but that would also be wrong. But least squares plays a very, very important role in here, and also in a lot of other disciplines. Being able to solve least squares problems will dramatically simplify your life. In terms of general least squares in Gauss-Newton, so basically every textbook on numeric calculus or optimization will cover least squares to some degree. Even you get an overview on open resources like Wikipedia, where you can have a look to if you want to dive a bit more into details and look up resources there. And depending on the community you're coming from, there are variants or a large zoo of literature on least squares using differently formal, using different notations. So even the notation that I used here may be different from the notation you're used to. And so there's a whole variety on how that may look like. And I want to point out the Probabilistic Robotics book on actually this relation of the least squares approach to probabilistic state estimation, where you can actually show what the similarity and differences are. So with this, I would say thank you very much for your attention, and I hope with this lecture you got an idea how least squares works, what you can do with it, and in the upcoming lecture we will actually use this tool in order to do useful computations with it, such as looking into the simultaneous localization and mapping problem from a graph perspective, and use least squares in order to find the most likely map configuration, for example. So with this, thank you very much for your attention, and see you soon. Thank you.